So the intuitive definition of a limit is pretty straightforward. You can see here x is approaching 2. Here from the lower side or from the left. And on this other part of this table, x is also approaching 2, but from the right. Okay, from higher values of x. And you can see what's going on with the function value. It's going to 4. That's a numerical approach. This would be a graphical approach, same function. As x approaches 2, y closes in on 4. Okay, so we say the limit as x approaches 2 of my function y or f of x is equal to 4. Here's your formal intuitive definition, I should say. And here we have a couple cases where the limit as x approaches a is always L. Here your function is well defined, right? In this case, the output is equal to the limit as x approaches a. Right? That is f of a and the limit are the same. Those two y values are the same. Here you can see the limit is up here while the function value is down here, but the limit's still L based on our intuitive definition. As x approaches a, y approaches L, even though f of a is down here. And in this case, f of a isn't even defined, but the limit still exists. The limit of the function, and this is true for all three cases, would be L. Okay, in this case, we can have, here's a new function. We got a numerical approach, and we can see it's going to 5. If we were to graph this, we have the same result, 0.5 rather. Okay, that is this function as the limit, f of x, I'll get to g of x in a second, but f of x is this guy. As x approaches 1, in this case, is equal to 0.5. So that's my L, the limit, and this is my A, the x value. Now let's define, so it's undefined when x equals 1, right? But the limit exists. That's really the point of this example. Now let's define an output when x equals 1. So the output is 2. Okay, but it doesn't affect the limit. The limit is still 0.5. All right, here's an interesting function. H, it's equal to 1 if t is positive, and 0 if t is negative. I should say it's equal to 1 if t is non-negative, 1 or 0 and greater. So we use this function to introduce the topic of right-handed and left-handed limits. In this example, the limit of this function h as t approaches 0 from the right, use a little plus superscript, and then we have a left-handed limit, the limit of my function as t approaches 0 from the left, are going to be different, right? As I come in from the right, values greater than t equals 0, I'm up here at 1. Right? As t gets really close to 0, whereas y get really close to 1. As I come in from the left, I'm down here at 0. Okay, so I have a right-handed limit and a left-handed limit. They're not the same. So in fact, the limit itself, right? You can think of this as a two-sided limit if there's no one-side notation to it. So the limit itself, we would say, does not exist. The right-handed and the left-handed have to be the same. Okay, so here's the notation and the definition. The limit is L if and only if the left-handed limit and the right-handed limit are both the same. Okay. Okay, so you can pause this video, see if you can figure out these limits. I'll go through them. The limit of this, so this function is g, piecewise defined. As x approaches 2 from the left, would be down here at 1. Part B, the limit of g as x approaches 2 from the right. Oh, I got that one wrong. Let's try again. The limit of this function as x approaches 2 from the left is up here at 3. From the right is down here at 1. So as x approaches 2, then, because they are not the same, these two numbers are not the same, does not exist. Let's look at 5. As we approach 5 from the left, we're up here at x or y equals 2. As we approach 5 from the right, we're up here at x equals 2. Which means since these are the same, the limit as you approach 5 is 2. Notice we're not interested in the output here, which is actually down at 1. We're interested in the limit. Okay, we have infinite limits to think about. That is your notation. What does this mean? As x approaches some value, if it's unbounded, well, you should think of the y value is unbounded. It shoots up to infinity, or maybe we could also have negative infinity. We'll see in a minute. Your function goes down. You should be thinking of asymptotes. Okay, so here you can see the graphical interpretation of that, right? As x approaches a, the function goes up to infinity, right? So this is undefined. The function, or rather, the function does not exist, right? But we can be a little more specific in kind of stating the reason. It's a different reason than why our function did not exist before. The right and the left existed, but they weren't the same. In this case, it's just unbounded. Okay, and you can also have negative infinity. Okay, here's a couple examples. Right-handed, left-handed limits with infinite limits. Okay, so as you come in from the right, or from the left rather, to some value x equals a, you can have unbounded function going up forever, goes to infinity. Right, and here's the case, right-handed limit infinity, left-handed limit negative infinity, right? As you approach it from the left, it goes down forever, negative infinity. As you approach some x value a, which is a vertical asymptote in all these cases, as you approach a from the right, in this case, the function goes down. All right, and these are all, like I said, they're going to be vertical asymptotes, all of these cases here. All right, how about this function? This is we already know how to do this one, right? That is, we know by our trig approach, we know that the tangent function was undefined when x equals pi over 2, and then 3 pi over 2, and then 5 pi over 2, and go in the opposite direction, negative pi over 2, negative 3 pi over 2, and so on. All right, so that's the same as your vertical asymptotes. We answered that question without really calculus, just by knowing the domain of the tangent function. All right, but if we wanted to, for practice, we could say the limit. Let's do a right-handed limit. If you can picture your tangent graph, and I'll sketch it in a second. What's the limit as x approaches pi over 2 from the left? Okay, and then I'll put my tangent function here. What's that equal to? Well, we got two approaches to this, okay? So I can do, so far we have two approaches for limits, the numerical approach or the graphical approach. The easiest thing to do is in your head, picture the tangent function and do a quick sketch of it. Remember this guy? And it's going to be period pi, so it'll repeat itself a lot. But if I'm only interested in x equals pi over 2, right, which is this vertical line right here, then as I approach that from the left, value smaller than that, as x approaches this from the left, what's y do? It goes up. So we can say that that's infinity. Okay, And there'd be another guy here. So we could do the other one just to see the limit as x approaches pi over 2 from the right of my tangent function is negative infinity. Okay, so the best I can do, what if I asked you this, the limit as x approaches pi over 2 of your tangent function, what's the best way to write that? Well, since as I come in from the left, it's going that way. As I come in from the right, it's going that way. There's nothing to really put here in terms of using infinity symbol. So the best we can do does not exist. Okay, note this also does not exist, but we'll use the infinity notation to kind of do a little bit better than does not exist. We can say it's unbounded. It's a vertical asymptote, and we can say which direction it's going. Okay, I won't spend a lot of time on the limit laws. These are pretty intuitive as well. If I can, let's explain one of them, the constant, or I'm sorry, let's do the constant multiple one. That is, if I have some constant times a function and I want the limit of that product, it's the same thing as pulling out that constant and just evaluating the limit of the function and then multiplying. Okay, we'll see the constant multiple rule. I think that's pretty straightforward. Then we have one for sums and for differences. That is, if I have two functions added together and I want to evaluate the limit, I can do them one at a time. Same thing with difference, product, and quotient, of course, provided that the limit in the denominator exists. Okay, so I'm going to skip this slide. We can, basically, this is an exercise in determining to use those properties, right? That is, as I figure out if I want to use the property, I just break it up, the limit and the limit, G. Okay, and I do one at a time. So as x goes to 2 for f, what are we at here? That's 1, 2, that's up there somewhere, right? So that would be, the limit and the function value are the same in this case, so we'll call that 1.5. And for g, as I approach 2, oh, that one's 0. Okay, good. So this one does not exist, right? Just because I do have a limit that's 0 there. All right, let's see. Here's some other properties that we'll go through. They're pretty straightforward. That is, if I want to take the limit of a function raised to the power, I can take the limit of the function and then raise to the power. Okay. The limit of a constant as x approaches some number is just going to be the constant, right? If it's always constant. And here you can think of this as kind of a simple substitution. The limit of my identity function x, y equals x, as x approaches some value a is going to be the same y value a. Okay, a couple more that we'll do these in examples. I don't think we need to go through each of the limit laws. So here we come up with my first, what I'm going to call analytical approach. Right? And we've talked about this before. That is, if there's nothing really going on at x equals a, then the limit and the output are the same. For example, let's say the limit of my function x squared as x approaches 1. That's just 1 squared. That is, I just plug it in, right? Because I know there's no issues with this quadratic function. All right. Like I said, a lot of times we won't be doing these more simple ones where you do direct substitution. We'll look at more interesting functions. Some limits are best calculated by first finding the left and the right. Following theorem says that a two-sided limit exists if and only if both one-sided limit exists are equal. I think we talked a bit about this already. That is, the left-handed has to be the right-handed, has to be that in order for the actual limit to exist. So in other words, we can use right-handed and left-handed limits to define the existence of a limit.